Today we will discuss about the special purpose electronic device. In that we will discuss the tunnel diode. Discuss the operation of tunnel diode. We should know the tunneling effect or quantum mechanical tunneling. Quantum mechanical tunneling refers to penetration of an electron through higher potential to lower potential energy. But quantum physics, it can be proved that an electron can move from lower to higher potential energy. Also, if width is or depth of the potential barrier is narrow. This tunnel diode works based on this tunneling effect, and this tunnel diode also looks like normal p diode, but the P and N regions or P and type materials both are heavily doped, and these P and N materials should be degenerate type semiconductors. Degenerate type means if Fermi level lies inside the conduction band, then that n-type metal is called degenerate type n-type semiconductor. If Fermi level lies inside the valency band, then the p-type metal is called degenerate p-type material. Yes. So when you are increasingly more doping in the n-type material, the Fermi level is moves inside the conduction band. Similarly, when we are increasing the more doping level in the p-type material, the Fermi level moves inside the valency band. Such kind of semiconductors are called degenerate type semiconductors. So to fabricate the tunnel diode, we must use the heavily doped degenerate type semiconductors. Junctions has very narrow depletion region of 100 angstroms. We know the depletion region is always depends on the doping levels of materials. Yes, the depletion width is more penetrates into the lightly doped regions. Here, both P and N regions are heavily doped degenerate type materials, so the depletion width is very narrow. Yes, it is approximately 1 by 50th of wavelength of the light. So here, the depletion width is narrow. Electrons can penetrate through this narrow depletion width even if potential energy barrier is present because of quantum mechanical tunneling. Here, electrons can penetrate through the narrow depletion width even if potential energy barrier is present because of quantum mechanical tunneling. Here we can discuss the operation of an tunnel diode with the help of energy band diagram. So first I am considering the in open circuit condition, that means we are not applying the any voltages to the P and N regions. In open circuit conditions, we know in P junction also the net current is 0. Yes. So here we are observing the energy band diagram. In this, Fermi level in the P side is at same energy as the Fermi level in N side. So here you can observe Fermi level in P side and Fermi level in P side, both N side and P side both are at same energy. So there are no field states on one side of the junction which are at the same energy as empty allowed states on the other side. Hence, at open circuit condition, there can be no flow of charge carriers across the junction. Therefore, current becomes 0. Yes. So here Fermi level of P and Fermi level of N are at same energy levels. So in this, any one of this side has no field states and the other side has no empty energy states. Therefore, electrons can not move or cannot cross the depletion region. Therefore, the current becomes zero in this open circuit condition. So it is normal. It is similar to the normal PN junction diode. Yes, here there is no current. Diode in reverse bias condition. So you can observe the energy band diagram here. When reverse bias is applied, energy level on N side will shift down. So N side will shift down. Then what happens? Fermi level is shifted down. Due to this, empty energy levels will be present in the conduction band in N region. So when it is shifting down, empty energy levels will be present in the conduction band in N region, opposite to the filled energy levels of valency band of P region. Due to this, electrons start tunneling from valency band of P region to conduction band of N region. So electrons are tunneling or moving from P region to N region. Valency band of P region to conduction band of N region, thereby tunneling current flow in opposite direction. So current is moving from N to P. If applied reverse voltage is increased, then electron tunneling keeps increasing. So you can observe here VI characteristics in this reverse bias. So we are increasing the reverse bias voltage, then current is also increased linearly. So in this reverse bias condition, the tunnel diode, when the tunnel diode is in reverse bias condition, then what happens? It behaves as a resistor. V and I are linearly increases, so it behaves as a resistor. So here you can observe the clearly energy band diagram. Yes, in forward bias. Assume that P region is 0 volts and negative voltage is applied on N region. Due to this, energy levels shifts upward direction by an amount of E into V in N region. So here you can observe the energy band diagram. Here energy levels shifts upwards. In this, if small forward bias is applied, then a few field energy levels in conduction band in N region will appear opposite to the empty levels in valency band of P region. Then electrons tunnel from conduction band of N region to valency band of P region, and a tunneling current flows in opposite direction. If applied forward bias voltage is increased, then electron tunneling increases. Tunneling current reaches maximum value. Then maximum number of field energy levels on N side opposite to empty levels of P side. So here we can observe in the diagram, when I are increasing the more positive, when I are increasing the more forward bias voltage, electron tunneling increases. Then tunneling current reaches maximum value. Then maximum number of field energy levels on N side are opposite to empty levels of P side. So electrons in the conduction band of N side will moves inside the valency band of P type material. If forward bias is further increases, then what happens? Then tunneling current starts decreases. So here you can observe, when I am increasing more, then what happens? So conduction band Fermi level is the energy levels are shifts upwards more than the possibility of electrons moving from conduction band to valence band in p region or decreases. So current will be decreases when I increase the more forward bias voltage. So tunneling current will be decreases. So you can observe here decreasing point. So the peak point is called peak point. It is the maximum current, maximum tunneling current, and decreasing. Then after again it will increases. That lower point is called valley point. If voltage increases further, then net barrier potential approximately zero, and thereby diffusion current starts flowing. That means holes are injected on N side and electrons are injected into P side. At a greater value of forward bias, tunnel diode will starts behave like a normal diode. So when you are increasing more forward bias voltage, the diffusion current will starts. That means it is normal operation of PN junction diode or normal PN junction diode. So that means holes are injected on N side and electrons are injected into P side. Yes. So for a greater values of forward bias, tunnel diode will start behaving like a normal PN diode. Yes. So the maximum tunneling current is P. That current is called peak current, and minimum tunneling current is called valley point or valley current. Yes. And after the valley point, it is working as a normal P injection diode forward bias. In reverse bias, so when I am increasing more reverse bias, so current also increases linearly. So it is behaving as a resistor. So in reverse bias, tunnel diode is behaving as a resistor. Yes. So tunnel diode, when it reaches to the valley point, when I increase the more forward bias, it reaches to the valley point. After that, it will work as a normal P injection diode. That current is due to the diffusion current. So from point origin to point P is the increasing current, it is tunneling current, and point P to V is decreasing current, it is also tunneling current, and point V to again it is increasing current, this is diffusion current. Yes. So this valley point is also nothing but cut-in voltage of normal p junction diode. Our normal p junction diode. So peak point is nothing but a point where the tunneling current becomes maximum in forward bias. Valley point is nothing but a point where tunneling current becomes minimum. Point B, this between point P and point B, it is decreases. That means the VI characteristics behaves negative slope. Therefore, the region of VI characteristics between peak and valley point is negative resistance region. So, tunnel diode is a negative resistance device. It implies that increases the increases in voltage and decrease in the current. So, we can say this tunnel diode is a negative resistance device. So where we are using this tunnel diode? Applications of tunnel diode. This tunnel diode is used as a high frequency switch because electrons tunneling occurs at speed of light. So here tunnel diode will work with the principle of tunneling effect. This in this electrons are tunneling with the speed of light, so the switching speed is more in the tunnel diode. So these kind of diodes will work in the high frequency switches, and tunnel diode is used in high frequency or microwave oscillators, and the tunnel diode symbol can be observed here. So it is looking like normal diode, but here we are represent the the tunnel symbol here, it is tunnel and anode and cathode. This is the operation of tunnel diode. Thank you.